Okay, let's start with a pretty scary thought. What if an AI, one that's supposed to be helping a doctor, remembers a drug's name, but completely forgets its life-threatening side effect? Yeah, that's a fatal flaw, and it's exactly what we're going to tackle today. We're diving into a new AI architecture called EAC-RAG, and it's designed to give medical AI a memory that isn't just powerful, but is actually safe. This quote from the research paper, wow, it just gets right to the heart of it. The word decapitate is so strong, but it's perfect. Imagine an AI reading a medical text and chopping it out for analysis. That single chop could literally separate a life-saving drug from a life-threatening warning, just because they happen to be a few sentences apart. That's the high-stakes problem we're here to solve. So let's put a proper name to this scary problem: contextual fragmentation. It's a huge challenge in retrieval augmented generation, RAG systems. That's the whole process of feeding an external document to an AI to give it knowledge it wasn't trained on. And to make that document digestible for the AI, we have to split it into smaller pieces or chunks. But this process is often totally blind to the meaning of the text. It might just slice a sentence right in half, splitting a drug from its dosage or a condition from its treatment. In the world of clinical AI, that's not just a small error, it's a potential catastrophe. So, how have we been trying to deal with this until now? Let's take a quick tour of what the paper calls the old guard, the common ways we chunk text today, and more importantly, where they fall short. All right, this slide really lays out the evolution of chunking. We started with the most basic approach, fixed size. Just chop the text every 512 tokens. It's fast, simple, but it has what you could call semantic blindness. It just doesn't care about meaning. Then we got a little smarter with recursive chunking. This method actually respects the document structure. It splits by paragraphs and then by sentences. It's a big improvement, for sure, but it can still miss those crucial connections that span across different sections. And that brings us to the really modern approach, semantic or agentic chunking. This uses a powerful AI to find the logical breakpoints. Sounds great, right? But as the paper points out, it is incredibly slow and expensive to run on an industrial scale. So you see the problem. Each step is an improvement, but none of them truly solve the core issue. And that, of course, brings us to our challenger. Let's introduce the core idea of this research: Entity Anchored Chunking, or EAC. And this isn't just another small step forward. It's a whole new way of looking at the problem. I just love this metaphor from the paper. Instead of blindly chopping text, EACRG first identifies the most important things, the medical entities, like drug names or diseases. And then it treats these entities like gravity hubs. All the related information, every side effect, every dosage instruction, becomes a satellite that's pulled into that entity's orbit. The context isn't something you hope to find later, it's captured right from the start, by design. Now you might be thinking, hey, this kind of sounds like GraphRag. And you're on the right track. But there are some absolutely crucial differences, which this slide illustrates perfectly. A traditional GraphRag uses a big, slow, expensive LLM to extract all the relationships during the initial processing. EAC-RAG, on the other hand, uses a super lightweight Scout just to find the entities. It saves all the heavy lifting for query time. The structure is also way simpler, just a hub-and-spoke model, which means you can plug and play new documents without having to reprocess your entire graph. It's a huge shift in efficiency. Okay, so how does this engine actually work under the hood? Let's pop it open and walk through the blueprint, starting with how it first ingests a document. The whole process has three main stages. First up, entity scouting. A fast, lightweight model just zips through the text and tags all the medical terms. Simple. Second, AVT segmentation. Now this is the really clever part, where the text gets split into chunks, but not just randomly. And third, graph construction. This is where it builds that simple but powerful bipartite graph, linking the entities, the hubs, to the text chunks where they live, the satellites. And this really is the million-dollar question, isn't it? I mean, if we're not using a big, expensive language model to read and understand the text, how on earth do we find the natural breakpoints? How do we avoid that semantic blindness we talked about earlier? Well, the answer is, surprisingly, mathematical. The process is called adaptive value thresholding, or AVT, and this graph shows it beautifully. Basically, the system slides a window of sentences across the document and calculates the semantic similarity between them. When the topic is consistent, that line stays high. But the moment the topic shifts, say from talking about symptoms to talking about treatments, the similarity plummets, creating what the paper calls a semantic valley. And any point that drops below that red threshold line, boom, that's where you split the text. And here's the formula that makes it all work. The really crucial part here is that the threshold isn't just some fixed number. It's dynamic. It actually adapts to the document itself, based on its own average similarity and standard deviation. This makes the whole process incredibly robust and, most importantly, computationally cheap. You're basically replacing expensive AI reasoning with fast, efficient math. So, once we have our nice, clean chunks, they get organized into this special structure, a bipartite knowledge evidence graph. Bipartite just means it has two parts. On one side, you have your knowledge, that's all the medical entities we found. On the other side, you have your evidence, the actual text chunks. The magic is that the links or edges only go between these two groups. An entity links to a chunk it's in, but one chunk doesn't directly link to another in this mean structure. And this illustrates the concept perfectly. On the left, you see the simple schematic, a central hub connected to its satellite chunks. And on the right, you see it in action in a real document. The entity asthma becomes a central hub, and it's connected to every single chunk of text where asthma is discussed, even if those chunks are spread across thousands of pages. All that context is now structurally linked together and ready to be accessed instantly. So, with this awesome structure in place, how does the system actually answer a question? Well, it uses this super efficient retrieval funnel. First, it identifies any entities in your query, like paracetamol. Then it takes a direct bipartite path, which is basically an instant lookup, to grab all the text chunks connected to that paracetamol hub. For more complex questions, it can do a multi-hop traversal, finding related drugs by seeing which ones share a text chunk. And only then, on this tiny pre-filtered set of candidates, does it perform a final vector search. And this is what changes the game. This architecture enables something the paper calls index-free discovery. Because the graph points you directly to the handful of relevant text chunks you need, you often don't even have to do a big, slow vector search across your entire document library. This makes retrieval incredibly fast and means the system can scale to enormous datasets without even breaking a sweat. Okay, but what if your query is a bit fuzzy? What if you search for steroids, but the graph only knows about corticosteroids? Well, that's where this really clever multi-tier fallback system comes in. Tier 1, latent anchor, will map your term to the closest entity it knows. Tier 2, constellation, gets a bit smarter and looks for chunks that contain a combination of entities from your query. And if all else fails, Tier 3 acts as a final safety net. It just performs a standard semantic search, but, and this is key, only across the high-quality chunks that were created by the AVT process. It's a really graceful way to make sure you always get a relevant answer. So, the theory is great, but does this thing actually work in the real world? Let's check out the results from a case study they ran on a huge clinical directory. The system was tested on a really dense, 3,450-page medical document. The entire ingesture process took just under 54 minutes. But here's the key takeaway. Look at the number of chunks. Instead of the estimated 30,000 fragmented bits and pieces a standard RAG system might create, EAC RAG produced just over 7,000 highly logical, semantically meaningful segments. That is a massive gain in both efficiency and quality. And here's the visual proof. These graphs show the relationships the system was able to preserve. On the left, it directly connects paracetamol to its known side effects and related drugs. On the right, it maps the concept of fever to all its related symptoms and treatments. This is exactly that critical context that traditional systems often decapitate. Here, it's not just preserved, it's the very backbone of the system. During the case study, the researchers actually found this fascinating problem they called the table trap. Think of a giant index table in the back of a textbook. In the graph, that one chunk becomes a super connector linking everything to everything else and basically diluting the meaning. But what's so cool is that the EAC-RIG structure made this problem obvious, and the researchers even proposed a solution for it. Just weight the connections so that specific paragraph-based evidence is always prioritized over those noisy index tables. So what's the big picture here? What's the major takeaway? Well, this research is proposing more than just a new technique. It's really suggesting a whole new paradigm for RAG. This slide really captures the essence of that shift. Traditional RAG is all about searching for context. You've got this messy pile of text chunks and maybe a separate graph, and you just hope you can piece the context back together after the fact. The information and its context are separate things. EAC RAG, on the other hand, is about possessing structure right from the beginning. The chunks themselves are defined by the graph. The fact and its context are totally inseparable by design. And we'll end with this powerful summary from the authors themselves. By building a system where context isn't just an afterthought, but the fundamental architecture, EAC RAG gives us a real roadmap for building AI that's more reliable, more explainable, and a whole lot safer. Which really leaves us with one big question. How soon will this shift from searching for context to possessing it become the new standard for all of our AI systems?